Okay, we now move to worksheet number 6, which is the help sheet, help video on Kepler's laws of period. During this, we'll be using the formula for Kepler's law, which says that r cubed on t squared for any system of orbits is equal to a constant. Now, that constant is only applying if we are all orbiting the same central mass. So all the planets going around the sun share the same constant, K. All of Jupiter's moons share the same constant because they're orbiting Jupiter's moons. And this constant is equal to gm on 4 pi squared if you want to use and work out the exact value of that constant. So moving on. Here, this is the first question, is just simply applying this formula. We want to find the period, we want to find how far it is from the centre of the Earth given the period. So we know that we want to use r cubed on t squared equaling 4 pi, that's not gm on 4 pi squared. Now we want to find r up here. To do that, it's probably best, before we substitute anything in, to get rid of the t down here and bring it up there. So it's easier to rearrange and say that that's t squared gm on 4 pi squared. Now let's check we've got all the information that we need to use this formula. We need the mass of the central object, which is that one there, and we need the period of orbit. So let's just work them out from the data. So the period is 2 hours, so it's given here as 2 hours. So t equals 2 hours, and the mass of the central object, capital M, is equal to 5.98 by 10 to the power of 24 kilograms. Now, for use in this formula, everything has to be in the correct metric units of seconds and kilograms and so on, and meters. So we are going to rearrange this to hours. This 2 hours has to be converted into seconds. So I'm going to leave that one for you to do there. Once we have those two values, we place them in for these. Don't forget at the end of all this that you will need to cube root whatever is up here. So don't forget to do that. Also, some other little tricks or common errors, I suppose more than anything else, that there was a square on the period there and there was a square on the pi there. Now, once you've found that distance r, we're then, in the second one, asked to find the altitude of the planet. To do the altitude of the planet, of course, the altitude of the satellite, we have to take into account, this is our satellite up here, that satellite, some things on it. We will know that that distance there is the radius of the orbit, which is r, but we want to find the altitude. The altitude is that there, the height. So to find the height, we need to subtract the radius of the planet. In this case, the radius of the Earth, which is 6,400 kilometres. So take a few moments now to work out A and B. Right, we now move to questions 2, 3 and 4. So it's 2, 3 and 4, as well as question 7 from the worksheet. These are all grouped together because they are continuing the same thing. The same thing in all cases here is to find the altitude. So we want the altitude there and radius. Okay. This last one is how far is Saturn from the Sun, and that's also the radius of orbit. So in all cases here, r cubed on t squared would equal gm on 4 pi squared. We want to find r in all cases. So rearranging that, we get r cubed equals, once again, t squared gm on 4 pi squared. The only problematic part is that the period here, the period period there is given in here as 24 hours. Geosynchronous orbit around Mars, we need to know the rotation. So geosynchronous orbit means it has the same period of rotation. So in this one here, we use a period of rotation of 24 hours and 39 minutes. This one here, the moon has a period of 23 days, and this one here has 29.46 years. In all cases, all of these need to be created into seconds. So here we simply would multiply by the appropriate 3,600 and so on. So I'm going to leave you to take a few moments to convert all of these periods into seconds and then pop them in and find your radius of orbit. Don't forget that if you're finding altitude, you must remove the radius of the planet. So take a few moments, pause the video. We now move to question 5, which is a compound question where we're finding no longer the radius, but we're trying to find one of the other factors in the formula. So once again, the formula is r cubed on t squared is equal to gm on 4 pi squared. And here, the first question is that we've got one of the moons of Mars, Phobos, has a mean orbital radius. So this time we are given r, and r is 9.4 by 10 to the 6. And you also have its period. That's how many seconds it takes to do a complete orbit. So there it is. This time we're actually asked to calculate firstly mass and then use some information to find something about the other moon, which is Deimos. So let's do part A first. To find the mass, we need to find this value over here. Once again, before using this formula, it's easier to rearrange the formula and then substitute in. So bringing this part here up and the g down, we get m on this side would equal 4 pi squared r on t squared, and the g comes down to make that. So it's 4 pi squared r on gt squared is the mass. So all we need to do is pop in all the values that we know, that r equals 9.4 by 10 to the 6, there it is, and t is 2.76 by 10 to the 4, and just check that all of these are the metric units. R is in meters and that is in seconds. So take a few moments now to do that. Just pause the video now before we go on to B. Right, we now work out the next part, which says another moon of Mars, Deimos, has a period of that. What is the radius of Deimos's orbit? Now, if we wanted to, we now know this part here, which is the second half of the formula. We know what gm on 4 pi squared is because we just calculated the mass of Mars. So we know that r cubed on t squared is equal to a constant. And that constant is the same no matter if it was for Phobos or for Deimos, because they are both orbiting the same planet. So we're going to work out what k is and then use that to work out the radius of orbit for Deimos. It should have a line there. So calculating that, so going up here, in the last question we should have organised, also worked out that the mass of Mars is equal to, let me see, it's 6.45 by 10 to the power of 23 kilograms. So gm on 4 pi squared, now that's the constant. So we're going to calculate that as 6.67 by 10 to the minus 11 times that mass up there, all over 4 pi squared. And that will give you a constant. So take a few moments now to calculate that constant. Now that you've calculated that constant, we know that no matter what, r cubed on t squared would equal that constant for every satellite that is orbiting Mars, because this is the constant for Mars. And we want to find the radius of Deimos' orbit, so r cubed would equal t squared k. So take a few moments to calculate by putting in the period now of 1.09 by 10 to the 5 seconds into that position there, and then cube rooting, you can now find the radius of Deimos' orbit. So take a few moments by pausing the video now. We move to question 6. Jupiter has a mass of 1.9 by 10 to the 27 kilograms, and there are two moons, Io and Europa. And the first thing we're asked to do is work out the constant, which is the GM on 4 pi squared. So once we've calculated that, we are actually calculating k. And now we've got k, it doesn't matter if I use the same k for Io or Europa, they both share this, because this is the constant for Jupiter. So now that you've got that, we know that for Io, the radius cubed for Io is equal over the period squared for Io would be the same as that k. And also it would equal the radius cubed for Europa over period squared for Europa. So all we need to do is use this same k. In part B, you're asked to find the orbital, from the orbital radius you need to find the period. And in part C, for Europa, we want to find the orbital period and then work out the orbital velocity. Now to find out the orbital velocity, we simply need to realise that we can use two ways of doing it. We could use just gm on r as the orbital velocity formula. That means that's the radius that we need, so therefore we would need to find out r here and pop it in to there. Or you can simply say that orbital velocity would be the distance divided by the time taken. And that distance is a circle, so it's 2 pi r. Either way, you get the same answer. So you can use the actual formula for orbital velocity, which is this one. Or we could simply use circle geometry and say, okay, the radius of Europa's orbit has to be, we need the radius anyway, so you need that one there. So let's go through that one. So using period, which is given as 3.55 days, you can find r, and then after you find that, you can do either way. Okay? So take a moment and either way use this formula up here, or we can use the second formula down here. We move to question 8 now. This is now a compound question, and it's asking different things for different reasons. So we have a satellite of mass 500 kilograms. It's orbiting the Earth at an altitude of 700 kilometres. What's the radius of the orbit of the satellite? This is just asking simply from previous information. That is 700 and that's 6,400. So we can work out what the radius of the orbit is. Now that we know the radius of the orbit, we can use r cubed on t squared equals gm on 4 pi squared to find the period of the satellite. So take a few moments after that to do that. To work out the velocity of the satellite in orbit, we have two methods. We can use the formula for orbital velocity, which is VO is the square root of gm on r. Or you could simply work out that v orbit is distance over time again. And the distance is the circumference, which is 2 pi r, over the period, which is just found in B. After you've done C, you can then, because this is the orbital velocity, this is the velocity of the satellite in an orbit, then you can work out the centripetal force, because we know that the centripetal force formula is mv squared on r, where v would be this v down here, the tangential velocity. R is the radius, because that's on the surface of the Earth, isn't it? R is the distance that the satellite is away from the centre, and m is the mass of the satellite, which is given to us up here as 500. Finally, E is asked us to find the gravitational force that the Earth exerts on the satellite, and we can sometimes do a lot more work than we really need. We could simply, if we weren't thinking, say that the gravitational force would be given by G m on r squared, where m and n here are the mass of the Earth and the mass of the satellite respectively, and r is the radius between them. Or we could realise that the gravitational force is the force that's causing this satellite to stay in orbit, so therefore it must equal the centripetal force. So we can simply restate this answer here. So just take a few moments to work out all A, B, C and D, and then realise if you want to, you should have a go and do it from first principles like that, and just make sure and confirm to yourself that the gravitational and the centripetal forces would be the same. And finally, our final question on our worksheet is another compound question. So it's a satellite which has a mass of 2,000 kilograms. It's in orbit around a planet. The radius of this orbit is given, it's 25,000, and it also has a period which is likely given to us in seconds. We need to find the mass of the planet, so it's asking us to select the correct formula, and since it's on the Kepler formula worksheet, we should just realise that that's what we're talking about. So it's r cubed on t squared equals gm on 4 pi squared. Once again, it's easier to manipulate the formula before the substitution goes in. So let's say that m is equal to 4 pi r squared. So let's try that again. 4 pi squared r cubed on gt squared. Once again, we go through the process that we know now the mass of the planet. We're now asked to find the velocity. Now the velocity is once again distance over time. And the distance is the radius, or 2 pi r, find the circumference, and divided by the time taken, which is the period. That will be the quickest because we are given g and we are given t. Or we could substitute that into the orbital velocity formula, which is the square root of g m on r. These will give you the same values, no matter which way you use it. Centripetal force is now used, and once again, the centripetal force is equal to mv squared on r. Please note that that's a lowercase m, and by definition, that's the object which is in motion to form that. Must be the satellite, and that V is just being calculated. So the compound question is where you have to use one value in front of the other to work the next one out. And finally, what gravitational force does the satellite exert on the planet? And what gravitational force does the planet exert on the satellite? And I'm not going to say anything more about these because I said it last time, and I want you to start thinking a bit more about these two questions here, and why these two values, in fact, the last three values, are shared in common. Okay, I hope this helps. Here are all the answers that we should have got, so you can check that any of them that you might have got wrong or I've got wrong, so please tell me if I have. Okay. Thank you very much for watching.